MEPSAnd, minimum area path surface analysis over n-dimensional surfaces, is this tool that we have developed in order to analyze energy surfaces in general with any number of dimensions. Like, for example, here you have a 3D, like the most used case, a 3D surface, but it can work with any number of dimensions. So when we think about a 3D surface, we are talking about two coordinates and in our energy values, like this example here. We could think of 4D surfaces as 3 coordinates and 1 energy value, and 5D surfaces as so on and so forth, like you get the idea. The thing is that the visualization is no longer trivial anymore. So MEPSAnd basically abstracts any of these as the same exact thing, like a set of points for which we have to infer some overall connectivity. And in order to do so, the user may use 3 methods to define this connectivity. First is the default one, which is let MEPSA assume that the user data follows a grid structure, which is basically the case most of the time. Alternatively, the user may provide, and MEPSA also provides by some good defaults. The user may provide one cutoff per dimension so that this cutoff can be used to infer which points are connected in which manner through which dimensions. And alternatively, if the users want to represent something more, a connectivity that is more complicated, they still have the opportunity to provide this connectivity in an explicit manner through an additional file that will basically point out which points are connected to which points explicitly. If the user follows the connectivity assignments that MEPSA provides, there is another choice that has to be made. Whether to allow these connectivities to happen in a diagonal fashion or not. By default, this is disabled, but what we refer to as diagonals here is pretty straightforward in our use case here, in our example here, because because you can think this as a diagonal in a typical 2D surface, but for any n-dimensional surfaces, here we are referring to diagonal as any connection through more than one coordinate. Once these choices have been made, basically MEPSAnd creates this surface connectivity network. That is the first graph that we are constructing from this surface. And based on this graph, the first step it follows is to try to identify which minima are located throughout this graph. So first of all, this starts at the point level. So point-wise, it tries to infer which points could be minima candidates, following these very simple rules, which basically is like if your point is connected to something that has higher energy, it can no longer be a minima. And if your point is, like this here, if it is connected to something with lower energy. So, and if your point is connected to basically points with the same energy, you're in a plateau, and we are not considering this for this initial detection. Once we have identified those candidates, we propagate through those candidates along points that are connected with the same energy level. And with this, once we have built these clusters, we evaluate the validity of these clusters as minima themselves. And those that pass this rule become our minimum clusters. Once we have defined these minimum clusters, we propagate from those minimum clusters upwards until we cannot find any higher energy points for each case. And we detect the overlapping points between the propagations of each of these clusters to identify barrier clusters. Once we have identified these barrier clusters and we have these minimum clusters, we can we can reduce the whole graph to a much simpler structure called the global network, which is just the connection between minima and barrier clusters. Minimum and barrier clusters, sorry. So just to give a graphical overview of this process, here we have a very smooth, very simple, all of this come from the examples that are provided in the website, but this is just the simplest that we provide. And this just contains 3 minima, all connected through barriers to each other. So the abstraction of this becomes this. This is an actual visualization that comes from MEPSAnd itself. And this is constructed via the network visualization using barriers as edges, as nodes. So basically we have 3 minima, these circles, and 3 barriers. In the 4D case, we know we are no longer showcasing the barriers explicitly. They are just encoded as edges. But you can see that the abstraction still holds. And for the 5D, for which we had no representation before, we can now at least visualize that we have different regions with different energies for all of these cases. Yep. So once MEPSAnd has built this global network, it is pretty much trivial to compute paths over this network because it is a very clear optimization job in which you have to identify the lowest barrier through which you have to pass until you connect the origin with the target. So in our case, the lowest barrier out of the 2 possible paths is 32.61, 32.04. So the choice is pretty evident. And basically, the next step is to translate this global network path to a surface connectivity network path. So basically a path that is explained or is described in actual points in our data set, in our original data set. That is what you see here below. This conversion, just briefly in order to understand one of the output files that we can obtain, is computed by creating combining fragments. Each of these fragments is describing the transition between each of these nodes, like between minimum and barrier to minimum, minimum to barrier, barrier to minimum. And you can see the fragments, and the combination of them all is constructing the final path that the user is getting. Another interesting feature that this graph abstraction provides is that we now have the ability to, in an analytical fashion, in an automated fashion, to basically block the highest barrier, the access to the highest barrier through a path in order to force a second round in which an alternative path must be sampled. And you can see here the example, like we sample our original lowest energy path, we block the access to the highest barrier, and we now compute this path again, and we block the access, and we can no longer reach the target. So this is something that can reach a finite number of possible paths. In this case, these 2 paths represent the first lower energy path, and then this alternative path. And we cannot identify any other paths other than this. Just as an example, here we have a more complicated surface. This is the Geneva-Turin example. This is topographical data just for the sake of having something noisy and complicated. But you get the idea of having your lowest energy path, the path that is going through the lowest barrier, and having all these possible paths which amount to 392 on top of our lowest barrier path. Yeah. So before we jump into the hands-on demo, I would like to point out a couple of good practices that are pretty relevant based on feedback that users have been giving us. And the first of them is that MEPSAnd is already designed to handle partially sampled data sets. By this, I mean that you don't have to uniformly sample every dimension equally. So you can leave unsampled points without any particular issue. And this is a built-in feature because this is a typical characteristic of n-dimensional surfaces. For example, in metadynamics, it's pretty common that you don't sample your whole sampling space at all. Like your system may sample some points and leave others unsampled. So if this is the case, do not use placeholder values. Just remove those points. Do not create these high energy values all throughout the non-sampled regions, or otherwise you may end up having the risk of creating a huge cluster outside of your sampled region that is basically connecting to everything around, and this is just going to create a lot of unnecessary RAM and CPU overhead for no good reason, no useful reason. Also, if possible, try to use surfaces that are as smooth as possible. Due to the nature of this abstraction, smoother surfaces are going to create sparser graphs that are going to, on one hand, accelerate the computations and reduce the memory usage, but also are going to produce easier to interpret results. For example, in the case of metadynamics, use bin sizes that make sense for the behavior of your simulation. Otherwise, you may end up having uninterpretable, unusable surfaces. So now we are going to jump into a really quick demo on how to install the software, how to perform the most common calculation, which is just a path calculation, and how to visualize the results here. So you can go to this website here, and you will find, if this video is seen in the future, this probably may change and will be updated because we keep updating this. But it is always going to contain the same thing: MEPSAnd, the source code itself, the program itself, the user manual, and your data samples. Like this, allow you to follow the examples that are described in the manual. So yeah, download all these three files, and let me make this a bit bigger. Yeah. You see that I already did that. I already have downloaded them. I already have extracted them. But let's start by going through the manual itself. So if you go to the manual, which is pretty extensive and covers many things that we are not going to cover in detail here, the first thing that you may be interested in doing is go into the requirements and installation. And here we describe 3 different strategies to install this, and these have been changing over versions in order to keep supporting newer requirements that we get from users. Right now, this seems to be working in Windows, Linux, and Mac OS, including the ARM Mac OS versions, which were quite challenging to get working for some reason, but some of these recipes should work for each of your needs. One thing to point out is that you may not be able to install the dependencies that are required for the network calculations, for the network visualizations, but yet the rest of the program is going to work fine, which is the most of the users are just going to use the other features, which is just the pathfinding itself. So even if you don't get these dependencies working on your setup, don't worry, you can still use the software for the most common needs. So here we see that we have to install, for example, using the Aconda package manager. We are going to use Micromamba here, but you could use any other package manager. And we are going to use the environment YML file that is being shipped with the zip file that can be downloaded. If you rather use pip, you still have the requirements txt file required, or you can just use an intermediate installation process in which some of them are installed via a Aconda package manager and some are installed via PIP. So this shouldn't take too long. By the way, what I did here, in case someone is not familiar with the terminal, I just got into the directory that was extracted from the MEPSA and the zip file, and I just did run the recipe that was described in the manual. So now we have our MEPSAnd environment, and we can activate it. And now we can run our MEPSAnd with this environment. So now we have this graphical user interface. That is the way we interact with MEPSAnd. We may develop the alternatives to this interface in the future, but it is something that is still on the planning table. So there are two things that we can do here. We can load a surface or load a session. Right now, I'm going to start by the basic way of interacting with this, which is loading your own data. So following the manual, if you want, you can go to the examples where, of course, you have a description of the whole algorithm and a step-by-step description of everything you can do. But let's this example for the sake of simplicity here. So this is the example I was describing before. This is a Geneva-Turin MDT dataset that basically is providing a point of a point of height every 20 meters. I don't remember. But anyway, this is just a topographic data. And we are just, for the sake of having something to compute, going to compute the lowest barrier path connecting Geneva with Turin. So this file is provided in the examples. And basically, we can go to the examples and load Geneva Turin. Yeah. So yeah, it is telling us that it is providing some cutoffs for us if we want to use them, but we are not going to. We are going to use the defaults, which is no diagonals, and we are going to assume grid-like connectivity. So now this is building the connectivity network that I described before. And once that's done, which is happening here on the background, the pathfinding pipeline is enabled. Okay. So now that we have here, the first thing that we have to do in order to identify a path here is to define our origin and our target. In a scenario in which you don't have any target or any origin points well defined, there are several things that you can do. First of all, is like you can actually visualize them, but you will see that this doesn't work well with complicated surfaces. Like if we go to the minima range here, you will see that we have an absurd amount of minima here. But you might be interested in some particular region because of your prior knowledge of your system, which is what we are going to emulate here, right? So here in the demo itself, you will see that we provide already the coordinates of Geneva and Turin, but here in your data of interest, you would know this information because it is your data of interest. So here we are going to define both ranges in such a way that we are going to fake that we don't know what we are looking for. And for example, we are going to look from a range of 6.14 to 6.16. And from a range of 6.21 to 46.21 to 46.23. Sorry. And we set this as the lower and as the origin. And you can see that we have selected the point with this index, which has this minimum index. We now set the target in a similar fashion. And we are just going to play the same guessing game as we did in the first case. We are going to assume that we don't know, and we are going to search from 7.5 to 7.7, for example. And from here, from here to here. Okay. All of this is explained in detail in the manual, and I'm not stopping because we are constrained on time. But if anyone has any questions or any issues running this, just let us know and write us an email, and we can help you. We have done that with several users already. So as you can see, we have computed the lowest energy path between those 2 points, and now we have to visualize it. One way to visualize it is to project it over whichever coordinates that we want. We can do this in a 2D or 3D fashion. Let's start with the 2D fashion. And we can use a contour plot, which is convenient here. This is enabled only when you are working with 3D surfaces. Otherwise, you are going just to stick to the plot version of this. So we can work with several levels of simplification on this path. We can start from a raw path here. And you can see this is basically taking any point that is covering these flat regions that the algorithm has no theoretical reason to discard. This is like the most exhaustive sampling method here, but we can also use the simplified path, which is the one that most people is actually interested in. That is just removing all those redundant stuff. You have an accurate description on how this is achieved in the manual. So on top of having this visualization that can be saved, we can plot it, for example, in 3D as well. Contour plot is no longer going to do anything in particular here, but you can see that we can visualize it in 3D as well. Not that is particularly useful in this case. We can also visualize the energy profile, and for example, we can compare the simplified path with the raw path that contains these flat regions, which is, this is a huge lake in the actual map. So the topographic data for that is just the same value, and that's why we have this super large plateau. So on top of, this visualization setup is just a convenience, but it is pretty limited. And there are much better solutions that can be used downstream. So the user has always the possibility of actually exporting the data that is being computed. This fragment-wise path is the path that explicitly describes the fragments that are being used to construct this, which is more complicated and beyond the point of this current demo. The simplified path, which is the one that most people is interested in, can be exported. And well, I already did that before. Let's overwrite it. Yes, yeah. And in order to showcase why this is relevant, you can see that we have the path that I computed and the surface that we are using. Our surface contains just the two coordinates and the energy or height in this particular case. And our path contains the index of the original point that is being visited regarding to the actual order that this point occupies, or the position that this point occupies on the original surface, the two coordinate values, and the height. So basically, we can post-process this as 1, 2, 3 image. We can visualize this on external software like GNU Plot. And for example, plot the coordinates of the points over this image that I created. For example, with line color green and line with two. Let's see how it's, yeah. And you can see that basically this could be your own Python or whatever post-processing pipeline, and you could create nicer figures because these are just parsable text files that can be imported with any regular tool like Pandas or whatever. So yeah, going back to our demo here, the last feature I would like to showcase here is the network projections, which is the more abstract, arguably. So right now we are going to try to visualize our global network directly, and we can do this by explicitly indicating that, explicitly showcasing barriers as vertices or not, as this is already a rather a complicated or rather convoluted surface. Let's keep them as no in order to reduce the complexity. And the problem that we are going to have is that, okay, now we have a as a network created, but in order to visualize it, we have to compute a layout that is useful. So let me showcase just one set of iterations of this relaxation, this forced relaxation of this layout. And I will load a nicer version afterwards because we don't have time. It will take us like 1 or 2 minutes to compute the full thing properly. But you see that it will slowly unfold until you have an extended, fully extended network. You can iterate on this, and it is automatically taking the previous step. So you can do smaller steps until you are satisfied with how extended this is. But plot. Okay, and you see that it's getting more and more relaxed. And there are many, there is a complete guide of how to edit this visualization that is going to, it is still beyond the scope of this demo. But just a few things to point out. You can export this graph to GraphML so that you can import it with external tools downstream to work with it in a more comfortable way. And also it is important that you can save your session at any particular point in time, and it will basically freeze the whole status of everything in memory so that you don't have to wait for these computations, these longer computations to actually take place. You can go back to where you left beforehand, which is what I'm going to do right now. I'm going to leave MEPSA. I'm going to close it. Now I have access to it again, and I will open it again. So I have nothing in memory anymore. And I'm going to load a session, and this session is going to be our session for Geneva Turin, which, by the way, contains, I forgot to mention that we could compute alternative paths. So this session contains already all the alternative paths computed, which is something that takes quite a few minutes. That's one of the things that I wanted to showcase with this one. Okay. And the other thing is that in the network projections, we have an already relaxed layout in which I have changed the width and the, so that you can see your, let's orient it in the same way. You can see your start at Geneva and your path to Turin in this network visualization. And cross without saving. And yes, I think it is easier to visualize this one. If we go to play, and you can see basically the whole thing. Like you can play with this until your data is visualized properly. Interestingly enough, this visualization will work no matter how many dimensions your data set has, as long as it doesn't get too convoluted to actually be usable, interpretable. But at least gives you some way to actually identify regions of interest through your data. And I think I can do that rather quickly. I want to load session. Let's showcase the 5D case, for example, just for the sake of it. And we have a path already calculated. That's good. So you see that I can pick 3 out of the 4 dimensions here and project the path on top of those dimensions. So this would allow you to interpret the meaning of this path on your whatever your coordinates represent. And of course, you can combine this in whichever way you want. Of course, you can still recover your energy throughout this path. And in the network projections, of course, after relaxing and after creating the path, but you can get a visualization that is usable to interpret the actual result you get. Yeah, it takes some time to render the heavier ones, but it should be, And you can see that, for example, I have only highlighted here the region that was sampled. That's the wild sampling computations that are described in the manual. And highlighting only that region, I have represented the path on top, and you can see these higher energy and lower energy regions along the path on top of your topology. And I think that with this, the demo and the whole thing is concluded.